Good morning, good evening, and good night, good afternoon, everybody. Thanks for jumping on again here. I want to get started right on time again today because we got a fairly long lecture to get through. Just a couple reminders. This lecture will be recorded and publicly released after the meeting, so keep that in mind. And also, if you have any questions during today's lecture, please post them on the Slack in the day 2 comms discussion channel. That'd be great. I don't know that I'll get to go through any of them during the lecture, but I will answer them during office hours, again at 1 to 3 today and 7 to 9, or in Slack, depending on the nature of the question. With that, let's dig right in. So yesterday's lecture was very much focused around a high-level overview of the project. Today we're going to really try to dig into the communications aspect of the Goby3 middleware. And I just want to review a few things from yesterday before we actually start writing code. We may recall that we have this 3-layer hierarchy that we're working with, and the 3 layers that we're looking at are inter-thread, so within a single process, thread-to-thread comms, so within a process. And then we've got inter-process, and this is within a vehicle, using 0MQ in our case. And the third is inter-vehicle, which is going to be within a squadron or cluster of vehicles. So keeping those 3 layers in mind, we're actually going to start in the middle of the hierarchy here at the inter-process layer. And the reason for that is because it's probably the most familiar to many of you if you've worked with ROS or Moose, LCM, or any of those other inter-process communication middlewares. Then we're going to work our way in to the inter-thread layer. And finally, we'll work on inter-vehicle, which is, we'll save that for last because it's the most complicated and also the most potentially valuable and most interesting of the 3. So we'll spend probably the better half of the second part of the lecture on inter-vehicle comms. But first, as I said, we'll start with inter-process. And at its simplest, if you're going to do inter-process comms, you need 2 processes. So a single publisher and a single subscriber is going to be your simplest topology. And if we look at that in graphical format, it's going to look something like that. Publisher publishes some type of data, subscriber subscribes to it and receives it. And this particular topology is what we'll look at for the first part of today's lecture. Because once you understand this, you can build it up pretty easily by using the same ideas. And just to be sort of more explicit about it for the moment, in Goby3 in our process, you've got Goby3 in the middle here as a broker. So what I drew there is simply, it looks actually a bit more like this, where you've got a publisher goes to Goby3 and then that sends it to the subscriber. But because this piece is somewhat transparent to the actual use of the system, I'll omit it from a good number of the figures, but keep in mind that it's always there in the actual communication path. And then once we go beyond this single publisher subscriber, in more realistic systems, you're looking at possibly having quite a large number of publishers and subscribers. You may have a publisher that subscribes, it's a publisher to data type 1 to 2 subscribers, 1A, 1B, and then another publisher for a different type of data, publisher 2 and a subscriber 2. And this is pretty frequent that you're going to have multiple subscribers to a particular publication, especially as regards to things like the vehicle's navigation information and stuff like that, where a lot of different pieces of code need to know where the vehicle thinks it is. And less frequently, you'll end up with a situation where you want to have multiple publishers of a single data type. which is going to look something like this. You've got two processes that publish the same data type 1, and then you've got two subscribers in this diagram. And so this is often used when you have a process that needs to spoof a particular data type, or you may have two sources of the same data stream at a different time. And so all of these general topologies are supported within the Goby3 interprocess layer. Okay, so now that we've got that kind of in our minds here, we're going to look at this first one, this publisher, single subscriber situation. So how do we do that? And as I said, we're looking at the process first. So you remember from the end of yesterday's lecture, we built up this pattern set of files that builds into this application. So in the source bin patterns directory, I've got the single thread pattern. This is which essentially we built up at the end of the lecture yesterday, and a multi-thread pattern. So for the lectures and probably for your homework, you're welcome to copy these as a starting point. And so what I'll do that now is essentially we'll make a directory for our example. Interprocess1 is what I'll call this first example. And then we can copy the code, this pattern code, into that for a publisher and also for a subscriber. And then in order to build this new interprocess1 directory, we're going to need to add a CMake list to it. And we're going to add subdirectory, the publisher, and for the subscriber. We also need to add to the parent CMake list, so up a directory and source bin. We're going to add the subdirectory for interprocess1. So now we've told the project level CMake list how to build our new two directories. Then, because we copied these out of the patterns folder, both of these, publisher and subscriber, are going to have the same binary name. So if I go into the CMake list for the publisher, and I change the name of the application that's built here from Goby3 course single thread pattern to interprocess1 publisher. And then the next thing to do is we'll go into the app.cpp, and everywhere here it's called single thread pattern. We'll just change this class name to be publisher, sort of generic. But again, if you're like writing a driver, like GPS driver, that's what you'd call it. But for this example, we'll just call the publisher and subscriber. And the last thing we need to do is changing that. Also change the name of the config object. That's, as you recall, in the config.proto. And I'll change the name of that message here, publisher. And so now we've converted our pattern application into one called publisher. And then I'll just quickly do the same thing for the subscriber. So go up into subscriber folder, change the CMake list to Goby3 course interprocess1 subscriber, open up the app.cpp, change everywhere that it's single thread pattern to subscriber, and open up config.proto and change this name of the configuration message to subscriber. And if you recall, the same class name, but it's in the namespace config, which is what distinguishes the configuration proto class from the application class, which is in Goby3 apps. Because again, this is a convention. You don't have to use it. You can name these differently if you want, but it makes it easy for me to quickly change them. All right, so let's make sure we got all that right. before we go on by building this. So as you recall from yesterday, there's this build.sh script that runs cmake followed by make for you automatically. You can use it or not as you will. So I'll run that to build these while we're continuing going on. So we just copied the to pattern, copy the single thread pattern into two new binaries, Goby3 course, the process, publisher, and subscriber. Okay, so while that builds, well, it's already built, so that's good, but we'll move on to a little bit of a side here. How we end up actually fully qualifying a publication in Goby. So to publish inside of Goby, you need actually 4 pieces of information. You need to know the layer that we want to publish on, and so that's interprocess in this particular case. So it could be intervehicle, could be interthread, but we're choosing to use interprocess right now. You need a thing called a group, which I'll talk about more in a minute, but this is a similar idea to the LCM channel, a ROS topic, or a moose variable. And then we need a marshalling scheme. And for this course, we're going to use protobuf for interprocess at least. We'll use DCCL for intervehicle. And the last piece is the data type that we want to actually publish. And this is within a particular scheme. So in the case of protobuf, this is equal to a message, particular message type, which the message then becomes a C++ class that inherits from Google protobuf or Google protobuf message. So those are equivalent, really. There's a C++ version and there's the proto version. But everything we'll see in the code is actually a C++ class. So I said there are 4 things that we need to know, which there are, but we've already basically picked 2 of these ahead of time. One is that we know we want to publish between processes, so we picked the layer, and the others we're going to use protobufs for everything, so we picked the marshalling scheme. So then it narrows it down to just 2 things that we actually still need to pick. And that's the group and the type or message. In this case, when we're using protobufs. Okay, so what's the point of the group? The group is really a way to collect several messages of a particular affiliated usage. So for example, if you had 2 GPS sensor drivers on a particular vehicle that were publishing GPS position, and you could publish them to 2 different groups. You could have GPS 1 and GPS 2. So the underlying data type is the same. This contains things probably like latitude, longitude, and the GPS position. But we're going to publish them for 2 different groups for the 2 different GPSs. So that's a case where you're going to segregate a single type into 2 different groups. And then the subscribers can choose whether they want to subscribe to both the GPSs or one or the other. Another option would be that these drivers also publish a GPS diagnostics message. And then we can either put this on a different group, or we can just also publish this to the same group, GPS 1 and GPS 2. So now we've kind of distinguished the data stream coming from a single GPS is on GPS 1, the group, and the second one's GPS 2. But this group contains actually multiple types of data. And so when the subscriber subscribes, it has to match all four of these things. So if you subscribe to interprocess, to the group GPS 1, to the marshalling scheme protobuf, to the data type GPS position, you'll get the GPS position from the first GPS. And so this gives you a fair bit of flexibility into how to segregate the data flow within your system. So I said they have to match. One thing I want to highlight now, because it becomes useful later, is that for the layer, publications on a particular layer, they're automatically published to all inner layers. So what I mean by that is if you publish a message on interprocess, it will also be automatically published on interthread. And if you publish on intervehicle, it will automatically be published on interprocess and interthread within that inner node. So it doesn't get sent over to the other vehicle and published inside, but within the vehicle that's publishing, all the inner layers get published too. And we'll get to see that in work here in a minute. Okay, so now we need to pick these two things. We need to pick a group and a type for our first publication. And first thing, we'll look at the groups. So you can store the groups in any header that you want. In this course, we'll store them all in src lib groups.h. So I just have a single file where we'll keep all the groups for this particular course, because it's a small project. But you could envision cases where you want to split this across different files, depending on the overall architecture of your code repository. So what is in a group? Well, first of all, a group specifically is an instantiation of a Goby middleware group class. And this group is, I think, can be thought of as a union, sort of, and I'm going to put this in quotes, it's not really, of a string and integer, and specifically a 1-byte integer, an unsigned 8-bit integer. And so on the high bandwidth layers, and by that I mean ones that it makes sense to send strings around, so that would be interthread, interprocess, the string is used. And then on low bandwidth layers, which in this case is going to be the intervehicle, the integer representation is used. And this may quickly make sense because if you're sending back messages of tens of bytes, there's no sense to send a whole string around just to represent what group it's in. So that's the purpose of the integer piece. And I should mention that it's actually, in the case of the high bandwidth layers, it's really the string plus the integer if it's specified. So it ends up looking something like, if you have this group here, it's Goby3 course USB nav, that's going to end up being sent as the string, including the numeric value as well. So it's sort of like a union, but sort of not as well. So let's take a look at some different group definitions. Some possible examples here include, you've got using declarative here so that I don't have to keep typing the Goby middleware part. So then sort of the basic group that you can have that just has a string component looks something like this. If you're not intending to use the group ever on a layer that needs an integer component, you can just omit it and you'll get an error if you try to use it. And then at that point, a compile error. So at that point, you can add it in if it makes sense. So this would be valid for interprocess and interthread. And then if I needed to use it for intervehicle, I could create, well, I just modify it, but I create a new group and call it foo2 if I want to. And then this is valid for all three of the layers that we're looking at here. And keep in mind that the string value is going to be foo:2 and the integer value is 2. You could also define a group with just a numeric value. And this is also valid for all three layers. Generally, I don't do this because the string value of 3 isn't all that meaningful, but it could make sense in situations where you're really not using this inside of the vehicle at all, and it's just for vehicle-to-vehicle comms. And just to drive a point home that about the numeric value is the only thing that's used on inter-vehicle. So these two are equivalent. So var is equivalent to var2 on inter-vehicle, but not on inter-process, inter-thread. And so I would avoid this situation. So just keep the groups unique in both string and integer representations, at least if they're going to be used for the same data type at any point in time. And then we'll get ahead of ourselves a little bit, but might as well introduce it at this point. There's a special case. The 0 is with this broadcast group, and that can also be thought of as no group, if you will, on the inter-vehicle layer. So if I define a group like so, or I have some string value and then I call broadcast group, which this just resolves to the value of 0. This basically means that on the inter-vehicle layer, I don't have any need to distinguish between different groupings of a particular data type, and I'll just save this base and not have any groups at all. And that's a fairly common situation, as you'll see in the homework as well. All right, so what are we going to send between our two vehicles? Let's just say we're going to send the vehicle's health. So that's the example we're going to look at for all this. So now that we want to send a vehicle's health, we need to create a group for sending this. So we'll call it health status. Put a message in there that includes the vehicle's health. And then the string value of this, I, by convention, tend to use the same name for the string as the namespace minus the groups. So I have this in Goby3 course, groups, health status. I just use the string as a representation of that. That's the same minus the groups. This is totally a convention. You can call this anything you want. Though I would suggest that you make it in some form represent the same thing as the instantiation in the code, or else things will get very confusing when you look at log files and the like. So one thing I haven't addressed here is why are these all const expression? So const expression objects, for those of you who are not familiar with C++ 11, not much, basically says that this object must be defined fully at compile time. And what this allows me to do then is to generate the publish subscribe graphs at compile time for static analysis. And that gives us the ability to analyze our system before even launching it. You can use runtime groups in Goby as well. They're referred to as dynamic groups. But I would avoid using them where you don't need to, because you lose the benefits of static analysis. Okay, so we created a group called health status. So that checks off one of the two items that we needed, which is the group. So now we need a type. And since we're using protobufs, that's going to be a protobuf message, which is the next section here. So again, by convention, I've kind of been storing the protobuf messages in this project in src lib messages. So within this directory, I've got a CMake list that's set up to build protos, and so far a couple of example protos. This is the one that's used to send a navigation and that trail example that you worked with yesterday. So in here, we'll just create a new message, and we'll call the message health status proto. And then, as I said yesterday, we're going to use proto2, which isn't required in Goby, but it keeps things consistent in this course, so we don't have to learn two different syntaxes. Put it in a package, which becomes a namespace, Goby3 course protobuf, and we'll call the message health status. So what do we want to know out of our vehicle's health? At a very minimum, we'll have an enumeration. That's what we'll start with. What's the health state of the vehicle? Is the vehicle good? Is everything running well? Is it degraded? Some stuff's failing, but we're not ready to abort a mission perhaps yet. Failing, like stuff's really not doing well, so maybe we should consider, unless it's very important, to keep going to stop the mission and recover. Or failed, like imminently the vehicle is going to have some kind of problem. So, you know, obviously these are just made up for this example, but you could have whatever you needed. And then once I've got this enumeration, I actually create a field using it. I'll call it health state, or state for the field name. And so that's my minimal little message. In a real system, you're obviously going to include a fair bit more information here. Things like subsystem health status, battery levels, specific failure data, error codes, whatever you think you want to know. Okay, so we've added this message. We also need to, like everything, tell CMake that we want it to build. Oops. So in the case of protos here, this protobuf generate CPP CMake macro. We just add our message to the end of this. And now it'll build our new message. Okay, so now we've created a group, which is this Goby3 course groups health status. And we've created our type, which is this protobuf message, Goby3 course protobuf health status. So we can start publishing. So let's go over back to our publisher code, which, as you recall, we put an src bin interprocess1 publisher. We open the app.cpp for that. All right. Let's assume that we want to send. Okay, so let's add messages to publisher. So let's say we want to send our health status at 1 Hertz. So as you recall from yesterday, we have this loop virtual method we can override, and we can call it at whatever frequency we pass to this constructor of the base class. So if I want to do it at 1 Hertz, I'll just put in here 1 Hertz. So now my loop is called at 1 Hertz. I'll clear this out because we don't need that there. Okay, so now within our loop method, we're going to create a health status message here. So we'll instantiate Goby3 course protobuf health status. And in order to use this, we need to actually include the header for it, which let's put it here, keep it together. So again, protobuf messages get compiled into the pb.h headers. Okay. And then we'll set the enumeration here to, right now we'll just assume our vehicle is good until we know otherwise. And for debugging purposes, we'll also write that out to glog. All the protobuf messages have this short debug string and debug string, which just returns a string representation of the message. Very handy for debugging. Okay, so now that we've got this message and we filled it in, which I realize is only one message field, but it's still filled in, we can publish it. And so recalling that we need 4 things to publish: the layer, the group, the scheme, and the type. How do we get those? How do we tell our code we want to do that? So the single thread application class here contains an inter-vehicle forwarder, which inside of that is an inter-process portal. Inside of that is an inter-thread transporter. And all those different pieces can be accessed by simply calling the base class method interprocess. And this returns a reference to the interprocess portal. And if you want an inter-thread or inter-vehicle, you just call inter-thread or inter-vehicle, and that would return the appropriate underlying classes reference to your portal or forwarder, which, remember from yesterday's lecture, there's different types of transporters based on whether you're at the edge or not of a node. So now, now that we call interprocess, that indicates we want to publish on interprocess layer because we're going to call publish on that interprocess portal. So then we can call publish. So let's look at the anatomy of publish here for a second. So I can call publish, and if I mouse over it, it'll show me all the template parameters. So we've got, I need to pass to the template parameters group, which we just defined. So we know what that is. Data, that's the type that we want to publish. Scheme, which is the marshalling scheme. And then to the runtime parameters, we have data, which is the actual message we're going to publish, and this optional publisher class that we will ignore for now and use when we get to the inter-vehicle layer. So of those things, we see everything we need to send it. So we've got a group, which is Goby3 course groups health status, which, as you remember, we just defined in the groups.h header. We've got our message type, Goby3 course protobuf health status. So that's our type. And then the scheme is Goby middleware marshalling scheme protobuf, which resolves to some integer. I believe it's a value of 1. And then once we have those, so these are the 4 things we need: the layer, the group, the type, and the scheme. We can pass in the actual message. Okay. Well, if I had to type all this every time I need to publish something, my fingers would tire. So we're not going to write this out every time explicitly. So you can take advantage of template deduction to remove most of this. So not surprisingly, the data type can be inferred from the fact that I'm passing health status message of the type protobuf health status. So this template parameter can be inferred. And then this template parameter, the protobuf scheme, can be inferred because each of the implementations in Goby for the marshalling schemes can infer the scheme ID from the underlying type. So we can actually just delete these two, and both of them will be inferred from the argument that we actually pass. So now we got something that's a good deal more readable, I guess, and less annoying to type. And so I would read this as, on the interprocess layer, publish to the group health status this message, which happens to be of the type protobuf health status using the scheme protocol buffers, if you want to sort of fully think it out. But really the things you're thinking about most of the time are, what am I publishing? What group is it going on? And what layer do I publish it on? The rest of it's inferred. Okay, so now that we've got that, might as well just build this to make sure I didn't mess up anything. And then we can go over to the subscriber and set up. No, that's not what I wanted. I want to split this. So we've got a publisher. Now we go over to the subscriber. It says an src bin interprocess 1 subscriber. And again, we'll open up the app.cpp. And here we don't have any use for the loop method. So we'll get rid of it, which means we can delete this and we can delete the definition of it. And since we're not using it, there's no point to even have it called by the base class. So we would just, the default is to never call loop. So I'll just remove entirely the base class explicit constructor arguments. Okay, so now we're going to subscribe. And where do we subscribe? In many cases, you want to subscribe to code on startup of your application. So that's what we'll do here. We'll subscribe in the constructor. So let me move that constructor out from being inline. Okay, so the anatomy, so the anatomy of the subscribe call is almost identical to the publish call. You're going to want access to the appropriate layer. So in this case, we're going to subscribe on interprocess, publish on interprocess. The two will match up. And if we call subscribe, what does this look like? So again, we've got the template parameters look almost identical. We've got a group that we want to subscribe to. We got the data type that we want to subscribe to, and the scheme. So those three are identical and in the same order as they are in publish. There's a necessity optional template parameter that is a work in progress, so we won't really use it this week, but the goal of that is to inform the static analysis system whether or not this subscription is considered required or optional or recommended for the vehicle's operation. So some processes will have things they'd like to subscribe to, but isn't essential for operation. Some things, if it's not being published by anyone, it means your system is misconfigured or incomplete. So that's what that field is. We won't use it, but it's sort of on the horizon. And then the arguments to it, the non-template parameters, the runtime parameters, is a callback function or a lambda. So that's what's going to be called when you actually get a piece of data that you subscribed for. And there's also an equivalent to the publisher optional metadata, which same as the publisher, we'll get to that when we talk about intervehicle. Okay, so this callback function or lambda, this is of the form standard function. And so standard functions can be constructed from a variety of function-like objects. My preference is to use lambdas because I think they're pretty easy to use and read compared to other options like standard bind, things like that. But keep in mind, you can use anything to subscribe for your subscription callback that can be converted into a standard function. All right, so let's put this aside for a second and actually create our callback. So what do we want to do when we get a message, a health status message in this case? Well, since this is a very simple example, what we're going to do is just write it to the debug log. So the lambda or any of the functions needs to be the signature void, the const reference of the message type. So in this case, health status. And while we're at it here, let's add that header. We have our health status message. So I'll have my health status message when this lambda is called, which will occur when I get a message of that that I subscribed for. And so in this case, all we'll do for this example is write this to the debug log. Of course, in real code, you're going to do something with this, which is going to be store it, process it, merge it with other data, take an action. I mean, this will become more clear in the homework what you'd actually want to do with these subscriptions. But for now, it's the comms work. We're just looking about how we're actually passing them around. So do something useful at this point with your health status message. Okay, so now we've got the lambda. So this is what we want to have happen when a message of our subscribe to type is received. And so then we can now actually subscribe for it. And here we've got to match the group the type. And the scheme. And the argument that we pass it is this lambda, which will be converted to a standard function and called whenever we get a type of that data. Again, this is a mouthful. For the same reasons, essentially, that we did it for the publisher, we can axe those. So now it says, when I subscribe to the group health status of the type that I put in the parameter line for my lambda, I want to have this called. So that, and then the protobuf is inferred from this type as well. So you can keep it short. Sometimes you actually have to specify the type explicitly when we start doing inter-vehicle stuff, but we'll get there when we do. So for now, for the simple cases, it can infer the compiler can infer the protobuf type from the parameter of your lambda. All right, so let's build this and try it out. And just let's go back to, whoops, that's the wrong screen. Come on. That's the screen. Okay. Go here. Here we are. So what we're going to actually be doing, in case this isn't clear, is we've now got this Goby3 course interprocess 1 publisher code that's publishing the health status message. Over to the Goby3 course interprocess 1 subscriber. All right, so let's switch up to terminal windows, and we will run a Goby3, which always mediates the comms between Goby processes, and we'll run the publisher, single V for debug one, or sorry, verbose mode, and you can see that it's publishing at 1 Hertz this health status message, and then the subscriber again at 1 Hertz receives the published message and also writes it out. So this isn't incredibly exciting, but this is kind of basic single publisher, single subscriber on the interprocess layer. Okay, so now that we've got that, we'll do the same thing on the inter-thread layer. So we're just going to convert the interprocess pair of applications into a single standalone process application. In case it's not obvious, I'm using the words process and application pretty much interchangeably here, with 2 threads that communicate to each other instead. So to do this, switch back up to the code and go into the src bin interprocess 1 directory. This is where we just wrote this code. I'll copy the subscriber for no particular reason, I'll copy one or the other, into a directory called interthread1, up a directory interthread1. Again, the usual add to the CMake lists. I need to add the subdirectory that I just created so that it'll actually compile, and then go into the interthread1 folder. Open the app.cpp and we'll change this subscriber now. We'll call this enter thread 1. Since this will be the wrapper application within which we'll have a subscriber and a publisher thread. Also config.proto. Change this to enter thread 1. And finally, the CMake list. Enter thread 1. Okay, so now we'll convert our single thread subscriber into a multi-thread application. So we can convert this by changing single thread into multi-thread, which includes the multi-thread application, which then gives us an inter-vehicle, inter-process, and inter-thread layer, whereas a single thread application has no inner layer for thread-to-thread publication. Okay, so let's go here. So in multi-thread application, we've got the thread type is inherits from a Goby middleware thread, of which there are several implementations. The one that we're going to use is Goby middleware simple thread. And all this is the implementation that is the three-layer hierarchy. Inter-thread, inter-process, inter-vehicle. If you had a different hierarchy, you would re-implement Goby middleware thread for whatever your hierarchy happened to be. Okay, so the class interface to thread is pretty much the same as the one as application. There's a loop method that's called optionally at a particular rate. There's access to inter-thread, inter-process, and inter-vehicle methods. And these return the appropriate transporter. And in the case of the secondary threads, these are all forwarders, inter-process forward, inter-vehicle forwarder. So the last thing that differs between these, the simple thread class and the application, is that we explicitly define and pass a construction to the constructor, a configuration object. So the configuration may differ from the parent application, or it may not, which is what we'll do here. So let's create those threads and copy the code that we had over. So we'll create a class called publisher that inherits from simple thread, which I'm going to type def up above here to, you can use the type defs or not, depending on your stylistic preference. And then much like the application, we pass a config object that we're going to use. In this case, we'll use the exact same config as the application, since for this particular situation, we're not actually going to use the configuration much at all yet. Okay, so I inherit from thread base, which is simple thread, create a constructor, which in this case takes const reference to the configuration type, which I need to pass to my base class as the first argument, and then the second argument. So this is slightly different than the applications, which the config is handled behind the scenes. The threads the configure is handled explicitly, which is because you may want to launch your threads with a subset of the configuration, or even entirely different configuration, and that's determined by the parent application. So then the second argument is where we specify our loop frequency, Again, 1 hertz is exactly what we had before. And then declare override on loop. Okay, and then for the subscriber, we'll have the same exact thing. We'll inherit from thread base, which is the simple thread with this thread 1, enter thread 1 configuration object. And again, we'll have this configuration passed in. Okay. All right, so there are all of our declarations. And now we just need to fill in the definitions for these. And we'll just basically copy over what we had before. So if we go to the publisher app, CPP, the interprocessor publisher, we'll just copy that loop method over to here. And the only thing that changes then is interthread, because we're now going to publish on the interthread layer. And similarly for the subscriber code, which I already copied because I used the subscriber as the starting point here. So we'll change this to the subscriber constructor. And then interprocess becomes interthread. So, so that pretty much changes the whole thing over to interthread instead of interprocess. And let me build this here to make sure I got that all right. So the last thing we need to do is we've defined these, but we need to actually launch the threads somewhere. And we can do that at any point during the interthread. There's my error. Goby3 course is the namespace, not Goby3. So we can launch our threads anywhere we want within the application, but typically, or not typically, sometimes we're going to want to do it in a constructor, and that's what we'll do in this case as well. Why am I doing well? Missing colons. So within the constructor for interthread 1, we will launch our threads. So constructor, and we will call launch thread. So when you call launch thread, you give it the thread name. So subscriber publisher in this case, something that inherits from ultimately thread or simple thread. And then for the argument, it's just the configuration for that thread, which is the same in this case as the parent class. So we will just pass that in. And similarly for the publisher. It's worth noting that the threads will be automatically joined upon a clean shutdown from Goby terminate. So you don't need to explicitly call join thread like in a destructor. But if you did ever want to join your threads during runtime, you can call pretty much the analogous with join thread. And that'll request that the thread join. It'll leave its loop method. And then once it's done that, assuming it actually ever leaves loop, it will join correctly and everything will work out. All right, so what did I mess up here? 151 out of line definition for subscriber does not match anything in here. All right. Subscriber, course app, subscriber. Must explicitly initialize thread base. Oh, there we are. Of course. So this is where it changes from the application to the thread, I have to explicitly include the configuration and then pass it to the base class. So thread base. So even though I'm not using the loop, I still need to pass the configuration through. So that was the last piece that we missed here. Okay, so then when we let that build, we can look and remind ourselves here what we actually are trying to create. So we've now had, as you see in the previous example, still up here, we had the interprocess1 publisher, which is a process publishing over through Goby3 to another process health status message. In this case, we're going to have the interthread1 is a process standalone, basically, that has two threads. One is a publisher, one's a subscriber, and it's otherwise we're publishing the same message between the two, this health status message. So we basically taken two processes and shrunk it down into one and did thread-to-thread publication. All right, so now that's built. That built, so we can run it. Go back up to the terminal windows here, stop our interprocess situation, and run a Goby3 still, because even though we're not using the interprocess comms in that multi-thread application, they exist. So it still requires connection to Goby3. There is a standalone class you can use if you really don't want even to use, if you just want interthread comms. And you'll look at that on the last day, I believe, a little bit. So then we'll just run our new application, which is this Goby3 course interthread one. And again, with -v for verbose. And here you're going to see now the interleaved. The publisher publishes and the subscriber receives, and they're in the same application. So they're on the same debug. So exact same thing, just inside of a process, thread to thread, interthread comms instead of process to process comms. All right, so with that, we're going to take a break, 5-minute break again. If you guys have any questions, please post them in Slack, and then we'll be back in about 5 minutes. Okay. While people are filtering back in, I'll take the opportunity to answer a couple of the questions that people have posted, because I think they're really good. Alex had asked that, like, I meant to mention that I do assume that the inner layer so he asked, is a safe assumption that each inner layer has more bandwidth than the next? And yes, that's actually an explicit assumption in the design of this middleware. And it's pretty safe to assume that's going to be the case. And that's why each layer would publish automatically. If you did have a hierarchy that wasn't true, in the design of the transporter for that, you could choose to break that, but I haven't thought of a model where that would be the case yet. So then Stephanie asked about the groups, what the integers indicate. So there's a string representation of the group and possibly an integer representation of the group. So each one of those would uniquely define the group. The integer representation is used for inter-vehicle comms to save bandwidth, which I think will become more clear when we get to that section a little bit later today. Chris had asked, what's a good real-world example of threads you might want to publish information between? And I think Jim Preissig actually gave a great answer to that. Basically, anytime you want to pass significant amounts of data relatively quickly, so acoustic data is a great example of that. So I have this network simulator that's built around Goby3 inter-thread, and I'm publishing audio samples around, so chunks of, say, 1,000 samples and over 8 channels at sampling rate of 96,000 hertz or something like that. And I want these messages, which are being processed, to be processed in quasi real time. So if I did that in interprocess, the overhead of serializing that, sending it over Ethernet, unserializing it, then processing it, doing it again between several different sections of the system would be too slow, basically. So my argument would be generally do interprocess, because I think it's a lot easier to debug and a lot easier to build. But it's part of why I did this example, to go from interprocess to interthread, because sometimes you realize what you've built really needs to have a tighter coupling because of the amount of data that you're trying to send around and the potential latencies you're willing to accept. You can then convert it into inside one process using interthread columns. All right, cool. So let's get going back on where we've left off. So before the break, we've been looking at this example here, where we had the single publisher, single subscriber inside of one process. So I'll quickly mention one thing. So yesterday I had told you guys that the interthread layer is implemented as shared pointers, and you may be like, there are no shared pointers here. And so that's true, because what essentially happens in this example, as I have it here, is this health status message ends up getting copied into a shared pointer when I call publish, which in some cases you may not want that copy. And so every publish and subscribe function has an overload that takes a shared pointer instead. And that's really for use on the interthread, but as you recall, every layer publishes inside of it as well. So in order for them to all line up, they all have to implement both of those overloads. So if I were to change this to use the shared pointer overload, it's going to look something like, now I've got a health status message pointer. Can use make shared to construct that pointer. So now I've got a shared pointer to a health status message instead of a health status message directly. And then I can dereference and call set state on there. So all the dots essentially become errors. And then I can publish my pointer. And this works because there's an overload for shared pointer for publish as well. And if I mouse over this now, you can see the data becomes shared pointer message to publish. It's one of these 3 overloads. And so now there's no copy of the object because I've declared a shared pointer. I've constructed it here, basically. I fill it in and then I publish it around. On the subscribe side, there's no point to switch to efficiency, but for symmetry, it might make sense. So then symmetrically, there's an overload that takes standard shared pointer of const tell status. And just to be very clear, I'll append PTR at the end of this. And now this is this pointer short debug string. So that's the that's the shared pointer overload for subscribe. Let's rebuild that, make sure that's it. So to be clear, for our tiny message here that has one field, this efficiency gain is totally inconsequential. But if you were sending megabytes or gigabytes, that copy could be quite expensive. So you're going to want to use the shared pointer from the beginning, just construct it once, and then publications will just pass around copies of the pointer rather than copies of the object. The last thing I want to mention on this is that, so we used a protobuf type here to publish on interthread, but since this message is not ever actually serialized, there's no need to use something like protobuf if you don't want to. You could pass around standard vectors, user-defined classes, structs, anything you want, because all we're doing at the end of the day is passing a pointer around. The other piece of that is once you've published this pointer here, you don't do anything with the contents of it. So let it go out of scope or whatever, because if you do change the contents of it, it's no longer a thread safe situation, and it will change on all the subscribers. So you have this implicit rule of thumb that if you're publishing a pointer, you're not allowed to change it once you publish it. So that's sort of part of the agreement that you make with the subscribers from here on out. So if you want to be really careful, if you want to make sure you really don't mess this up, then you can scope it so that publish is the last thing you do in a scope. Of course, in this loop method, it is the last thing I do. So something like that. That issue doesn't come in play if you don't use a shared pointer overload, because if there's a copy and you can do whatever you want with your local copy if you wanted to, but it's the price you pay, right? Okay, so so let's look at the fact that if I publish this on interprocess, it will be available also on interthread. So I can change this to interprocess, rebuild this, and then essentially run this graph. So if we look back at the whiteboard here, so we'll do let's call this cross layer. So interthread and interprocess. So what I did is I changed the publication to publish on interprocess, which also publishes on interthread. And so then we're going to now run this graph, basically, which is we've got this interthread one application that we were just running. It's got a thread called publisher, which is now publishing on interprocess. The thread subscriber will still get it because it publishes on the inner layer. But then if we run our interprocess one subscriber from before, because we're using the same type, group, and scheme, it'll also receive the message. So what does that look like? We go back over here to the terminal window. We got our Goby3 running. And then we've got our interthread one application running. So that looks the same as before because this publisher and subscriber are still receiving the message. And then if we were to run our subscriber from before, we're going to see the messages also show up over here. And that's because I switched the publication to be interprocess. So this demos that, with a single publication call on the outermost layer that I want to use, I can subscribe to it both inside that process and also outside the process. And This is especially useful on inter-vehicle publications because you might have data that you're going to publish to other vehicles that you also want to use internally. It's a convenience really more than a necessity. And that's the design convenience. And again, as you know, in response to Alex's question, that's very much because we're assuming that each inner layer has more throughput, substantially more in most cases than the outer layers. All right. Now we get to go to the fun layer, inter-vehicle. So we've done the kind of two inner layers of this three that we're looking at, and we'll look at the outermost layer here of our three-layer onion. So this is for slow links, and by that I mean, let's say very arbitrarily less than 1 megabit per second. Often much less. You know, so satellite comms, acoustic modems, that sort of thing. And so we build this layer on code that's, if anyone's used Goby2's ACOMS libraries, it's roughly the same set of components. And what those components look like in Goby3 is this graph. So you've got DCCL, which is Dynamic Compact Control Language, we'll look at a bit. It's a marshalling scheme built around protobuf that allows you to encode even tighter messages with more bounds than protobuf itself does. It's a dynamic buffer layer, which is priority queuing based off of both an overall priority and a time sensitivity or deadline. Then we've got one or more modem drivers, depending on what physical layer links you have on your vehicles. And then each one of these may or may not use the Goby medium access control. So like modems like the Hui micromodem need to be driven by an external MAC scheme. If your underlying link has a MAC scheme, you won't need that. So it's sort of an optional component here. And so using it from the code, from a publish subscribe standpoint, at its simplest, the inter-vehicle layer is much the same as the two inner layers that we've already built up. And that's where we'll start, but eventually we'll build it up to have some more tools that allow us to deal with drop packets, acknowledgements, and the low throughputs that we often see on these links. So what we'll start is we'll copy our inter-process code here from before. So we have this publisher subscriber pair in inter-process 1. So we'll copy that into a folder called inter-vehicle 1, keep consistent here. And of course, CMake must be informed of this. Let's clean this up a little bit here. And again, we're going to want to change those names because I copied them out of the inter-process publisher. So if we open up those CMake lists, so within inter-vehicle 1 publisher, we'll change this one from inter-process 1 to be called inter-vehicle 1. And similarly, in the subscriber, we'll change the name of that to be inter-vehicle 1. So the inter-vehicle 1, or not the inter-vehicle layer, has the most restrictions due to the low throughput that we've got here, and often fixed packet sizes as well on the underlying physical layers. So while on the inter-thread layer, you can publish any type because it's just shared pointer movement. On the inter-process layer, you can publish any serializable type with some implemented marshalling schemes, for example, protocol buffers. But protobuf messages are variable sized. They can be very short, very long, depending on repeated fields. So there's no upper bound on a protobuf message size, really. So that's a big part of why we're going to switch to using DCCL. So currently, the inter-vehicle layer, the only implemented scheme for it in Goby is DCCL itself. There's no reason you couldn't implement another scheme, but it would need to be suitable for use on acoustic modems, which is fixed packet sizes and very compact source encoding. So DCCL, what is DCCL? Take a minute to look at that. So it's another open source project that spun off from Goby3. It lives at libdccl.org, or the documentation does. The code lives on GitHub. So it's a language for marshaling object-based messages for extremely low throughput links. And I originally designed it for use with acoustic modems, but I found use for it in other places in the communities, especially as regards to satellite or degraded land-based links. So radio in situations that are subpar. So really, one way to think about it, it's suitable for use whenever you have a situation where having a very compact message is much more important than the speed of compressing and encoding and decoding those messages, because there's really not much thought putting into efficiently encoding them, and there's a fair amount of cost to some of these encoders. So that's the 1 megabits per second, very arbitrary layer. Think about it as that. Less than that, start thinking about DCCL. Higher than that, maybe not. Use protobuf or something else. So DCCL started as part of Goby. It was defined originally in XML, and then later I rewrote it using protobuf as the starting language. So nowadays, the DCCL3, which is the latest version, you can think of it as an alternative encoding for protobuf. As protobuf definition. And so DCL3 is the current version. Coincidentally, Goby3, they're not tied anymore to each other. Okay, so say we have a plain protobuf message. We'll just come up with this basic navigation report. So I've got a message navigation report. It's got 3 double fields, X, Y, and Z. It's got vehicle class, AUV, USV, or ship, and some Boolean value, battery okay. This is similar to the nav report message we're using for this course, but a little bit simpler even than that one. So given this basic protobuf message, if I want to turn it into a DCCL message, what I end up doing is, let me just copy this here so you can see both of them at once. So this is protobuf. We'll call it vanilla protobuf. And then if we turn this into DCCL, we have essentially a header. We import the DCCL option extensions, which provides the additional metadata for DCCL. And then we have some message level metadata, which is going to be in this option DCCL message. And there are a number of things we can set here. We always want to set the codec version. That determines the wire version of DCCL, which for all new messages should be 3 for DCCL3. A message ID, and what this does is maps the message name navigation report now into the number 124. There's an ID table for public use that you can request from if you want to share your DCCL messages. If you're going to use it internally, you can use any of them. And then there's sort of a private field. So 124 to 255 are for private use. And so you could use those for debugging and stuff. So that's why we're using 124 and up. That's no particular other good reason for this course. Since I'm not mixing us with another system, we could use any of them. And then the last thing in the message level metadata that we're usually going to define is the max bytes. So this is how big I'm willing to let this message get. And this usually allows you to target to some sort of minimum maximum transmission unit. So if you've got a modem that sends messages in packets of 32, you can set this to 32. DCCL does not packetize or fragment messages, and neither does Goby, and that's by design. We can talk more about that later if anyone's curious. So the max bytes is not the size of the message, it's the largest size that we will allow it to be before DCCL gives us an error. And so now we got the message level metadata, we can provide field level metadata. So we have DCCL.field, and for numeric fields, generally we're going to provide a minimum value, a maximum value, and a precision And this just says that I want this field is going to be from plus or minus 10,000 meters in this case. And we'll look at the unit stuff a bit more later. With a precision of 1, that's just tenths. So number of decimal digits after the integers. So precision 2 would be hundredths, minus 1 would be tens, and so forth. So we can do this. We'll just make the y field the same bounds. The depth field will set to meters from 0 to 5,000 meters. We don't need to know that to tenths. I mean, this is totally based on what you want to know on your operator side. And then enumerations are inherently bounded, so there's no additional metadata that you need, and same for Booleans. So now this message is a sort of well-defined protobuf or DCCL message in protocol buffers. And what we'll do is just for demo purposes, I'll make a new message here. We'll just nav proto, copy it in here and save it so that I can run now the DCCL tool on it. Okay. So DCCL comes with a tool called DCCL. You do --help, you can see all the things you can do with it. We're going to use the analyze feature, which provides us information about the message. So if I do DCCL-A for analyze, and then I can run it on a proto file, or I can run it on a shared library that contains compiled proto files. In this case, I'll run it straight on the file, which is this proto file, and this nav proto I just saved. And I've got a typo, line 10, expected semicolon. Or my semicolon's missing here at the end of this options. Okay, so then once I get my syntax right, it's telling me that this is message number 124, so that's the message ID. The actual size of the message is 8 bytes. Here's how it's allocated in bits between the header and the body. And each field in bits is this number of bits. So and then once it's done, it'll pad it to integer bytes, because almost every physical link deals with bytes, not bits. So, this allows me to tweak the fields in the message and see how they change. So if I decide that I don't need to operate in as big a region, I can change those values, and then the X and Y fields go down to 15 bits instead of 18, and the whole message shrinks by a byte. So this analyze tool is very handy when you're designing DCCL messages. And if I go into the project that we're working on, Goby3 course source lib and messages, this navigation message is already a well-defined DCCL message. And it's very similar to that example, except there's timestamp, vehicle ID, some speed, headings, and whatnot. So I can also run that analyze feature on the DCCL tool against this and see that this message is 13 bytes. And again, the allocation by field in bits for each field. Okay. So now let's take our health status message that we have. Let's close this. Don't need that anymore. If I open up the health status message that we were using, this one from before, let's turn it into a DCCL message. So we need to import the DCCL option extensions protobuf message from DCCL, which provides those metadata definitions. And we're going to give it the message level metadata. And codec version 3, always be 3. ID of 125, because the nav message is already 124, so we'll just increment that. So the message IDs need to be unique within a system, if that isn't clear. Otherwise, your messages will collide. And if they're loaded at compile time, all of them, then you'll get an error at runtime. So you at least will get that level, but you need to be unique. And then if we're going to use units, we'll also provide the unit system that we're using, in this case SI. And I'm not doing well with the semicolons today. Okay, so this is actually now a well-defined DCCL message because the enumeration field is inherently bounded by the fact that we enumerate the values. So if we look at that now with the DCCL analyze tool, we'll find that the whole message is 2 bytes. So there's a 1 byte header, and well, the body is only 2 bits because we're only sending 4 enumerated values. So it pads to another byte. So the whole message becomes 2 bytes. And as we add new fields here, those will get added to this as well. Okay, so now we have our type and our scheme. So we've got our health status has been turned into a DCCL message now. We need to do a little bit of work with the group. So as you recall, the groups are in source lib groups. Open up that file again. So as I mentioned earlier when we were talking about the groups, in order to use the group on the intervehicle layer, it needs to have an integer representation. So the simplest one is kind of the non-group group, which is the broadcast group, which says, I don't need grouping for this message type on the intervehicle layer. And in the homework, you'll take a look at a case where you'll use multiple groups on the intervehicle layer, so a numeric instead of broadcast group. We're using the simplest setup right now first. Okay, so the next step is we need to set up Goby3. So Goby3 has an intervehicle portal, as I mentioned yesterday. Somebody needs to actually be connected to the modems. And it makes sense for Goby3 to do that job as well. There's no real requirement for it, but it's a logical place to put it. So if we go into the launch folder of Goby3 course, let's create a new directory for our configuration, and we'll create one for vehicle 1's configuration and one for vehicle 2's configuration. And for this first example, we're going to end up using the UDP multicast driver. So let's do this, setting up the intervehicle portal. So we created some configuration directories. And now we need to pick a driver. We'll talk about these drivers a bit more later. But the one we're going to use is UDP multicast, which sends messages over, as the name suggests, over UDP, and uses the UDP multicast groups. So you can test this with any IP-based network, a loopback or Ethernet. It's very handy for simulation and prototyping. It's also can be used on real systems where UDP is a reasonable thing to use. So Wi-Fi or high throughput satellite links. All right, so given that we're going to use the UDP multicast driver, we'll go into the Goby3 configuration, or create one rather, for vehicle 1. And the vehicle 1 config, we'll create a file for configuring Goby3, the pv.cfg by convention for the extension. So I need interprocess configuration because I'm going to run 2 Goby3s instead of just 1. So we'll call the first vehicle VH1, and then I need to configure the intervehicle link. So if you ever want to know everything you can put in this file, remember you can run a particular Goby process with -e for example config, and it will write out everything you could possibly configure your process with, which for the intervehicle link is quite long because it's all the config for all the modem drivers. So sometimes it's easier to start with a short example, then reference this to see what you're missing, things like that. So intervehicle, we got to define at least one physical link that it connects to. The vehicle is given an identification, a numeric ID on the link, which is kind of like an IP address, sort of. And there's also needs to be a subnet mask, which is how Goby distinguishes which data goes over which link. And so we'll just use this is a subnet mask of FF00. And so if, and very much like IP network subnet masking, if the mask plus the modem and logical and the modem ID are the same, those IDs are on the same subnet. With a single link like we're using now, you could set the subnet mask to anything, because it doesn't really matter. Well, anything bigger than FFFF, I guess. So as long as you can include two IDs in it. So then we define what modem driver we're going to use to connect to our physical link, which in this case is the UDP multicast driver. And then that requires some of its own specific configuration. So there's a config for each of these drivers. This one's down here somewhere. There it is. So within that config, we've got to define a multicast address, which you can look up the valid address ranges for multicast on your own, but I just picked one kind of at random. And then there's a port. And so for those of you who aren't familiar with multicast, if you use the same address in the same port within something that's got multicast enabled, like loopback usually, or a local Ethernet adapter, all the clients, or whatever you want to call them, that are bound to that port and address will receive the message. Okay, and then I'm going to define a maximum frame size here, which is actually unnecessary because I will shrink it down even more in the max cycle. So since we're using this multicast driver to simulate an acoustic link, I'm going to set up a medium access control scheme that is much more like what you'd see on an acoustic modem. So the Goby supports a couple of MAC types. The one that we're going to almost always use is this fixed decentralized, which means every vehicle keeps its own clock and keeps track of the start and stop of slots based on its own clock, which means the clocks need to be roughly synchronized in some form using either oscillator or some kind of onboard timekeeping, like a controlled oscillator or CSAC, like a chip scale clock or something like that. So anyways, we're going to have two slots for this max scheme. We're going to have them, they're going to be 10 seconds long, and we're going to send up to 128 bytes in each. And then the second vehicle will send. So this is simple TDMA. 10 seconds is way, like any reasonable UDP link is going to have a lot more throughput than this, but this is to sort of simulate an acoustic modem perhaps here with 128 bytes rather than every 10 seconds. Okay, so then the next vehicle is identical, so with a few small changes. So we'll copy this configuration over to vehicle 2, and then if we go in there, we can open that up. The only thing that's going to change here is the name of the vehicle. So we need a different interprocess platform so that the correct processes connect to the correct OBDs, and we'll give this a different modem ID too, for lack of anything. Otherwise, everything's the same. It's the same max cycle because these need to match. We use the same multicast address because those need to match if we want to communicate. Okay, so now that we got Goby3 configured, we can go back to our code, the inter-vehicle code. So back in SRC bin, inter-vehicle 1 publisher. If I open my app.cpp, we can change where we're publishing on interprocess to publish on inter-vehicle. And then over in the subscriber, we can do a similar thing. So we're almost there. So before we're ready to do this, let's take another aside and talk about subscription forwarding. So the idea of subscription forwarding is that if everything we published on the inter-vehicle layer was just indiscriminately sent over all the acoustic modems or other slow links that we've got, we quickly overload them with data that may not even be used. So we take advantage of this idea of subscription forwarding, where you take, if you have a subscription, it's sent as a message to all prospective publishers. And until a publisher gets a message that says there's actually a subscriber at this location, the published data doesn't go anywhere. It's essentially thrown away when it reaches the inter-vehicle portal. And so what this looks like, here, if I see here, so we end up with a publisher that publishes a data 1 message, then a data 2 message. And I apologize that HackMD seems to have issues with sequence diagrams, but this tag belongs with this arrow. So until the publisher receives the subscription message, the data are just thrown away, or they're published on interprocess internally, but they're never sent outside the vehicle. And then once there's a subscription message sent over to the publisher, those data version copies 3 and 4, every subsequent message is actually sent over the slow link. So that's the idea. So in order to do this, how do we know where to send the subscription messages? So we sort of push the problem over to the subscriber. And one choice would be you could flood all of your links with all subscriptions, trying to find potential subscribers, which as a default option is not particularly good. So with some reluctance, we make this the problem of the application writer, who's going to have some idea of where the potential subscribers may be. You could set up some scheme that's as complicated or as simple as you want. And I'm happy to talk through some more of those complicated situations if people are interested in office hours. But at its simplest, we assume that a priori we know what potential publishers we may have. And that's what we're going to do here. So how do we do that in the code? So that's the subscriber object. Is the second argument to subscribe, is where we pass that information. So that's not in this overload, which means I need to add back in the explicit definition of the message. And now I've got the overload that has the subscriber. And then I configure my subscriber. So first of all, I will define my subscriber. So that's a Goby middleware subscriber. And this is sort of a metadata class, if you will. It gives me provide information about how I want to subscribe to this message. So the template parameter is the same as the message I'm subscribing to. And I'll give this health status subscriber name, health status subscriber. And then I need to configure it with something. So the configuration for this is, if I look at this, if I peek at this, I can see that this takes a transporter configuration and some other stuff we'll get to later, optionally. So I'll define a transporter config. I'll call this my subscriber config. And then I can do subscriber config. All the configuration is for intervehicle is in this intervehicle submessage, which in protobuf, to access that, to set it, you have to call mutable, which provides a pointer to that. And then within that, I can then add my publisher IDs, respective publishers. Right now, we'll hard code it. Generally, we'll send it over in a config file or discover it through some discovery mechanism. And so this says, I believe that publisher 1 might have the data I want. So I want to send my subscription message through the acoustic modem, or in this case, UDP multicast, over to publisher 1. Once publisher vehicle 1 gets it, it'll start publishing the data and actually sending it over to us. So let's get add subscriber config to my subscriber. And finally, I will actually put the right subscriber. What is this? Health status subscriber. All right, cool. So now if we build this, we should be ready to try it. Okay. So while that builds, oh, yep. Let's take a look again at what we're doing. So what we're going to be actually running here is we now have 2 vehicles. Each one has a single process that's publishing over over the inter-vehicle link to the other vehicle subscriber. So that's taking that same model we had, process to process, thread to thread, and then now doing it vehicle to vehicle. So while that's setting up here, we'll also close this, explore adding launch files. So as you saw, if you did the homework yesterday, there are these files that we can create, launch files that tell Goby launch what we want to launch. So at their simplest, we can create one that launches launches a Goby3 and launches our publisher process, which you see I pass over the command line which Goby3 I want to connect to, the one on vehicle 1 in this case. And then pretty much the same for vehicle 2. Copy that over as a starting point. And then the publisher here is going to be the subscriber, and it's going to be on vehicle 2. And the configuration for Goby3 is the vehicle 2 config Goby3. So let me just make sure I got those right. I got vehicle 1's launch file, Goby3 on vehicle 1, publisher connecting to vehicle 1, and then vehicle 2. I've got Goby3 on vehicle 2, and then the subscriber connecting to vehicle 2. All right. So now those, keep those full screened. Back up here, everything built, so that's good. And so we can actually launch them. And to launch Goby launch files, we run Goby launch on them, not surprisingly. So if I go back into that launch directory I was in, I can run Goby launch and then the launch file. So in this case, vehicle 1.launch. Okay, apparently not. What do I got here? Let's see. Well, that's getting closer. What do we got here in this config that's wrong? And instead of max frame size, that should be max frame bytes. So if I go into vehicle 1 config, Goby3, these should be max frame bytes. And then change the same thing in vehicle 2's config. Okay, and just put in the interpreter line, launch vehicle 1 launch. Okay, now that's running fine. Then we can run vehicle 2 launch, and that's running. Okay, so if you had noticed in the homework yesterday, we can, each one of these is running on a screen. So I've got my 2 Goby3s and I've got my publisher and my subscriber. So if I want to actually look at any of these screens, I can do screen-R to reattach to a screen. So I want to reattach to the vehicle 1's subscriber and or publisher rather, the vehicle 1 publisher, and I want to attach to the vehicle 2 subscriber. Okay, so you can see while I was futzing with this, it already received a bunch of messages. And the other thing you'll notice here is that these messages are going to come in batches every 20 seconds because of our TDMA cycle. Vehicle 1 sends 10 seconds, vehicle 2 sends 10 seconds. So every 20 seconds, we'll get a whole bunch of these messages. So this is the simplest version of inter-vehicle that's analogous to the inter-process and inter-thread comms, but it's not quite what we'd want in a lot of cases. So we may not want like 10 messages that say I'm good, because really what we really want to know is maybe the latest one, that so you don't use up all of our our bandwidth sending 10 or 20 copies of the same thing. So this is where we'll switch to talking a little bit about the dynamic buffer in Goby, which is where we can configure this kind of information. So the Goby3 buffer is a priority queue that combines two elements, an overall base priority value and a time-sensitive priority, which is governed around a time to live, or TTL. So let's assume for a second we have 3 message types, 1, 2, and 3. Well, these could correspond to TCTL IDs, but for now we're just saying we have 3 generic message types. One is going to have a base value of 1 and a TTL, or time to live, of 1,000 seconds. So assume this is vehicle status, perhaps some kind of relatively benign message that we want to get somewhat frequently, but not critically. Message 2 is going to have double that base value and a TTL that's longer. So this could be something it's overall more important, that double the base value, but it's less time sensitive. So maybe some sort of sensor data, something pretty important to get, but it's not that important to get it really quickly. And then message type 3, we'll call this base value 1, so the same as the first one, and a TTL of 3,000 seconds. So the same relative importance of the status message, but even less time sensitive. So this could be like debug engineering data, or perhaps health status if good, or nominal, or whatever you want to call it, something like that. So these values in the TTLs are going to depend entirely on your system design and trying to motivate these arbitrary numbers a little bit. So then if I had those 3 values, and I had a vehicle that transmits every 100 seconds, I get this graph. Basically, let's make that a little bit bigger for you guys. That's a little bit small. So if I transmit every 100 seconds with these three message types, 1, 2, and 3, every time a message is sent, its value is reset, and then it grows with a slope relative to the TTL. So the longer the TTL, the less the slope. So the slope is more gradual on this less priority message. And so what you end up behavior-wise is sending an interleave series of messages that balances the base values and the time to lives. We'll look more at that in homework, but I'll at least introduce that. There's a bunch of other stuff that you can also configure in the dynamic buffer. And so let's just take a look at the whole protobuf message. So this dynamic buffer config message is in Goby and source ACOM's protobuf directory. And so we can set, do we want an acknowledgement for this message? Yes or no. A blackout time, which is how many seconds between messages do I want to definitely not send a new one? So that's like a hard limit on, if this is 10, you'll send messages from that queue no more often than once every 10 seconds, regardless of the priority values. So hard constraint essentially that overrides the TTL and value base. A maximum queue size, so how many messages you buffer before you start throwing them out if they can't be sent or acknowledged. The queue order, so newest first is going to be a first in last out queue, and newest first false is going to be a first in first out queue. So you can configure any of those, and the defaults are shown here where it says default, and that's what we've been using in this example. So we have a queue of 1,000 messages with no acknowledgements, and sort of center of the road 100 value base and 30-minute TTL. All right. So since we only have one message, changing the value base will have no effect. But let's change something that would and see what happens. So if we go back over to the code here in our subscriber. So these buffer values could be set on either the subscriber or the publisher, and either one will take effect if you set them on both. There is rules about merging and precedence that are commented here, generally averaged So in this case, we'll access the buffer config, which is just another piece of the subscriber config message, in the same inter-vehicle submessage, but within the buffer message. And then within this buffer config, I can set all of these things that you just saw. So I can set the TTL, for example, and with units gives me the boost units representation. So if I want to set this to 5 seconds, whoops, I can set the TTL to 5 seconds. So now if I build this again and rerun it, we'll see something a bit different. So that build, bring these down. Two built, so I can now kick these off. And then again, we'll reattach the screen sessions so I can see what my publisher and my subscriber are doing. And so I haven't gotten anything on the subscriber yet because they're still waiting to get that subscription forwarding messages through. And there's my first set of messages. So see here, once we get the next set. Okay, now actually build those. Let's change. No, not. I missed getting that. Let's save this file first. Let's try that again. Oh, so yeah, I know what I did here. So that due to time, I skipped the section where I'm setting the timestamp in this message. So the TTL is actually set not when the message is generated, but when it's buffered. We'll look at this again tomorrow when I have more time to add the timestamp in, or you can read the lecture notes. But what we expect to have happen essentially is that each of these messages that are older than 5 seconds is going to get discarded. But in order to do that, we have to actually set a timestamp on our DCCL message. So we can look at that. We'll look at that during tomorrow's lecture. So there's a few more things I want to go through. I realize that it's almost the end of the 2 hours. So if anyone feels like they need to drop off, please by all means do so. The recording will be up later. For the rest of you, if you want to stay on, I'll finish up these last couple of sections, and then you can continue on your way. Okay, so what we want to do essentially is there's a couple other things that we may want to know. So does our message actually get there? I think is a big one. So for acknowledgements, true or false, essentially. So going back to our publisher code, we're going to take additional advantage of another feature of the publisher class, which we haven't used yet, but that's the second parameter here to publish, which is the ability to add acknowledgement callbacks. So we get whether we've gotten data or whether our data is expired before it's reached another vehicle. So these callbacks look pretty similar to the subscription callbacks. So look, one for expire looks like this essentially, which is we're going to have, it's going to provide us with the underlying original message that expired, an object of expired data, which contains metadata about when the message expired and why. And then here we'll just spit out a glog warning if our messages expire. And then the acknowledgement callback looks very much the same, except that instead of expire, we get this act data message. And in this case, we'll also write out. So this callback will be called if our message expires, and this one will be called if our message is acknowledged. And so where do we put this? Well, we create a publisher object, which is very similar to the subscriber that you saw a minute ago for this kind of metadata. And again, we have to pass it the underlying message that we're planning to publish. Publisher, that's what I'll call it. And we'll have publisher config. Am I in the right? I'm not in the right place. Yes, I am. Enter vehicle 1. That's why it didn't work. I changed the wrong publisher code, I think. Anyways, now that we're in the right place here, enter vehicle 1 publisher. Publisher config. The second parameter is the ACK, and the third one is the expire. And I actually have to create this publisher config that I thought I had done previously. Oh, that was a subscriber, right? So the publisher config here, we're going to set the ACK required to true, which is basically we want each one of these messages to be sent and resent until we get a positive acknowledgement over the physical link from the other vehicle. So given that, we can now compile this. And rerun it. And while we're waiting for this to compile, I can mention there's an analogous set of expire and acknowledgement callbacks available on the subscriber side, which would allow you to see whether your forwarded subscriptions ever reached potential publishers or not. So the forwarded subscription is basically just a special type of publication. And so you can, if you want on the subscriber side, add similar methods to these, which are mentioned in the notes, that will inform your application as to whether or not the forwarded subscriptions actually reached anybody. And between those two, you can have full knowledge within your code as to whether or not your messages are getting anywhere, or whether they're being lost either at the physical link or anywhere in between, in the water and things like that. Okay, now if that's built, go back over here, rerun the same mission, and now if we open up this, okay, that's not doing anything either. Okay. What did I do wrong? This is the enter vehicle 1 publisher. And oh, here's what I did wrong. So I defined a publisher, but I didn't actually provide it when I called publisher. So that's kind of important, or else it just sits there and does nothing. I have to add it to the second argument of my publish call. Okay, those are built. Go back over here, restart these. Okay, so now you're seeing this warning that our data expired, and the reason is expired no subscribers, and that's given until it received the first subscription forwarding message. And then let me expand this publisher side again. After we get So every time we send the messages, the subscriber link will send an acknowledgement back, and then we get this callback that says our message was acknowledged, and which message and what the latency was is there as well. So that you could build things within your code to a variety of things that would be useful to know whether or not messages are getting through. Change your vehicle's behavior, try to get into a better position for comms, surface and send over a different link, all kinds of potential adaptive behaviors you may want to do based on whether your messages are actually getting where you expect them to or not. And that's how you would access that in the code. Okay, so now that we've got those callbacks, I want to talk a little bit about the different modem drivers available inside of Goby. So at this point in time, there are 8 drivers in the open source distribution. That's Goby3, obviously. And these drivers are, we've got one for the Hui micromodem, both versions 1 and 2, the Iridium 9523 SAT modem, and similar ones use the same RUDIX and SPD protocols. We've got the shore side of the Iridium links, so they're RUDIX shore side servers, as well as the direct IP, which is the shore side version of short burst data, or SPD. There's one for the Benthos ATM 900 series. There's a new one for the Dell Research Propoda modem. And then there's the 2 UDP ones. There's the point-to-point one, which is kind of the point-to-point variant of the multicast one. Tends to one. This is what we're using now. And that's what we'll use to simulate for this week's course as well. And the final one is this demo driver, it's ABC driver, which is for a fake made-up modem, which shows how to write the new drivers in a minimal way. So I really encourage any of you who are using these modems or have new modems and want to use it at Goby, either adopt the driver or write a new one, depending on whether it's available, because there's continual change from vendors, and some of these drivers have seen more testing than others and are more full featured. And so, like, I don't even have access to all this hardware at any given time. So, that's a place that if anyone wants to really contribute back to the Goby community, it could be very valuable. To essentially adopt the driver, maintain it, update it, and add new features. And so if you write a new driver or you feel like adopting one, you can email me, you can put up a pull request on GitHub if you've got some code you want to look at. And please don't worry if it's not finished enough. I will help you work through it and get it to a state where it's a good contribution to the project. And so, a couple points along this week, I'll try to, this is an easy entry place for people to contribute back as well. So I want to show you guys the same example running over the Hui micromodem. So what I've got here is a little emulator box from Hui. It's basically 2 modems that are connected via coax cables instead of transducers, and then over serial to my computer. So what we need to do with that is, it's pretty straightforward change here. So if we go back up here to the launch files configuration for Goby3, so and enter vehicle one config. So we'll change this from the UDP multicast driver to the Hui micromodem driver. And then this configuration block is no longer meaningful. We'll have a serial port that we want to connect to, USB 0, a baud rate, which defaults on the micromodem to 19200. And then you can add any number of micromodem specific config to this submessage. And the only one I'll add is the one that resets all the NVRAM settings every time it launches. But here's where you'd add things if you're familiar using the micromodem, their NVRAM configuration and stuff like that. And the other thing we'll do is since the micromodem driver supports rate values, so these are just numeric mappings to a number of bytes, we use rate 1, which is 192 bytes per packet. And then we do the same thing over in the other one, the other driver config. The only difference is we'll connect to the other serial port. And we just also need to change the MAC configuration to use rate 1 micromodem. Okay, so that's otherwise then, as long as this is on, and we'll just double check that I got these modems connected. So if I open them up on serial, I should see some amount of output after a bit. So there's the heartbeat from modem 1. And modem 2, the heartbeat from modem 2. Okay, so those are good. Now I can launch, again, my vehicle 1 launch file, and vehicle 2 launch file. Look at the publisher, and again, look at the subscriber. Okay, so we're still waiting to get the subscription forwarded message over. This will take a little bit more time because the modem has to start up and all that. So while we're waiting for this to go, we may want to see some more information about what's going on with the actual modem, because this is pretty opaque. If I had some issue debugging the modem, I don't see any of the messages that are coming from the modem. Okay, so there's our first batch of messages that came over through the micromodem. So this is going to look pretty much identical to what we just ran, just now it's going through a real modem. And so if I want to add some more debugging information here, we'll open up these Goby3 windows and add in app block. So debug 2 is pretty verbose amount of debugging information, and show this little ncurses GUI as well. So if I add that to the Goby3 configs and then run them, close this down and restart them. Then if I reattach my screen now to like vehicle 1's Goby3, for example, I get this little ncurses window, which if I maximize it, now I can see over here the serial feed for the modem and the in and out feed split out to the driver with some annotation what these messages mean. So if you're familiar with the micromodem, this will be familiar. That's an incoming data packet. And then this is the medium access control scheme. So you can see every 10 seconds we send from 1, every 10 seconds we send from 2. This is some data. This is the inter-vehicle layers debug data. And this is the dynamic buffers priority contest. Every time there's a chance to send, it does this contest, picks the highest priorities based on the TTL and the base value, and sends those. And so if you look at the Goby3 for the other side, it's going to look nearly identical, with the exception that the priority queues will be different, and then this will send on 2 instead of on 1, and receive messages from the other. So that's how to switch. I want to show you quickly. It's a very small amount of change to go from running with a simulation and a debug driver, the UP multicast driver, to running with real hardware when you have it. Of course, now I can't run with warp because this real modem doesn't support that and things like that. So you have to trade off the real hardware in the loop versus the ability to run it faster than real time and things like that. Okay, so the last thing I'm going to go through today is to dig into a little bit more with this trail example that you guys ran in the homework yesterday, and we'll be using a good deal more today. So we now have the background to dig into the code here. So returning to this trail example, which if you remember is some number of AUVs trailing one USV, which communicates to a topside ship shore station. And so The current comms topology then, now that we know the inter-vehicle layer terminology, looks something like this. We've got vehicle 0, AUV1, AUV0, and then all the rest of the AUVs are the same. I just drew it at 3. At the top side, and then the USV. And so the thin lines represent the ACOMS link, and the bold lines represent the satellite link, both of which are simulated using the UDP multicast driver, but could be quickly swapped, as I showed, for a real micromodem on this, say, an Iridium, or perhaps a IP-based satellite comms link for the USV to the top side. And so these are the groups we're using: USV nav and AUV nav. So if we go back to the groups.h header, you can see these defined here. USV nav is the USV nav 1 and AUV nav 2. The full namespace is also included. I just removed it off this figure so it didn't get too cluttered as well. So the message that's used, so the groups we're using are as I see, is AUV nav and USV nav. And to reiterate, the 1 and the 2 is what's used when we're actually sending it over the slow link. In this case, the modems, and then the string value, this whole thing is what's used internally on the interprocess layer. And then the message type that we're using is this navigation report. And this navigation report message is defined in Goby3 course, src lib messages, where I'm putting all the protobuf messages. That's this nav DCCL message. So look at nav DCCL. Here's a navigation report. Here's the protobuf and DCCL metadata for all the fields. And this also includes the boost units definitions for the field dimensions as well. Okay, so how is this actually, where is the code that does this? And so we've got these 3 applications that are they're all, I'm just calling them the AUV manager, the USB manager, and the topside manager. And each of these pieces of code are responsible for publishing and subscribing the appropriate upstream and downstream messages. So expanding this previous figure a little bit, including the these manager code, we've got on the USB, so blowing up that box, on the AUV, blowing up this box, and on the top side, blowing up this box, we've got the these manager codes that are actually publishing, subscribing the particular navigation messages. So the AUV publishes its nav over to the USB and subscribes for the USV's nav because it needs to know where the USB is to trail it. The USB then takes the AUV nav and republishes it over the other link to the top side, as well as publishes its own nav, also subscribed to by the top side. And the top side takes both of these navigation messages and displays them via the OpenCPN and Google Earth Joe viewers. So if we look at the code quickly here, where these are defined are all in src bin in this manager subdirectory, and respectively the AUV manager, topside manager, and USB managers are in each of these folders. So if we look at the AUV manager, app.cpp, you can see that I defined 2 methods to subscribe to our navigation, which is coming off the front seat interface, which we'll look at tomorrow, and to subscribe to the USB nav so that we can trail the USB nav, the USB vehicle. Subscribe to our nav is an interprocess subscription to node status, which we'll look a lot more at tomorrow, but this is the message coming from the front seat control computer that is assumed to be computing our navigation solution, turns that into this DCCL message, this navigation report one, which is essentially copying a subset of the fields that are in node status. Then once it does that, it provides some debugging output and republishes that message now as the DCCL message on the AUV nav group on the inter-vehicle layer. And the buffer parameters are determined by the return of this function. So if you look into the nav publisher function, you'll see the publisher object that's created and setting the appropriate buffer parameters for that. And then the other function is the subscribe USV nav, where on the inter-vehicle layer, it adds a potential publisher as the USV. This set broadcast we haven't seen, but this just says, I don't need my own copy of this message. Broadcast it on this link to everyone who's in listening range. So the USV only has to send one message, and all of the AVs that can pick it up within broadcast range will receive it and trail it. Because if they miss one, you just want the next accurate updated one. You don't want to keep resending to each of the vehicles. So that's also why ACK required is false. Max Q of 1, I only want to keep the latest message. I always want the newest nav status, so also newest first. These are sort of redundant. There's no reason to have a queue of 1 if newest first, but there's also no reason to queue stuff you're never going to want. So I often pair these together for messages that I want a single latest message of. No ACK, 1 queue, newest first. So then once I receive a message from the USV, I'm going to republish it on interprocess, and this is going to go over to the IVP Helm autonomy system. And again, we'll look at that tomorrow. So basically, this manager is all just kind of a broker of sorts for messages. So it subscribes for data coming from the front seat, publishes it out on the inter-vehicle layer, which is this one, and then subscribes for messages coming in from the inter-vehicle layer on the USV, publishes it over to another process, which in this case sends it over to the autonomy system, P-Helm IVP. P-Helm IVP takes the position data of the USV and trails it, provides desired heading, depth, and speed outputs to trail the USV. And again, we'll look at how that works more tomorrow. So then the next step up in this is the USV. If I look at the code for the manager and the USV, it's almost a mirror image. We're also subscribing to the navigation coming off of the USV's front seat computer, so the navigation data for that, and publishing that out again on the inter-vehicle layer as the DCCL message. Same message, different group. So we're using the USV nav group. And this is how we're distinguishing between navigation from the USV versus navigation from the AUV on the top side. And then the mirror image, instead of subscribing to the USV nav, it's subscribing to the AUV nav. So this one's a little different because it's going to subscribe to all of the AUVs as potential publishers for their nav. And once it receives them, it republishes them on the inter-vehicle layer, which then will be picked up by the top side because the USV has both a link undersea, assumed to have an acoustic modem and a satellite modem to the top side. And that's that. So that's the last piece of this, of these three, is the top side. So if I look into the top side manager code, this is going to subscribe to the navigation messages, subscribe to the USV nav messages, and subscribe on inter-vehicle to the AED nav messages. In both cases, it calls this handle incoming nav function. And in handle incoming nav, it puts out some debug information, converts it back into the node status message, which is sort of the richer format, and republishes that on the interprocess layer to be used by the two viewers, because the OpenCPN interface and the Jove interface both subscribe to the node status message, which is a protobuf node status type, and then take those and pass it over to Google Earth and into OpenCPN. So those are the three pieces of code that implement this hierarchy of message passing, where you have messages from the AUV to the USV. Both of these get sent to the top side, and the USV also subscribes, or the AUV, excuse me, subscribes to the USV data so that it can trail the USV. So that's how that works. And so tomorrow we'll look into the autonomy pieces, the front seat interface, as well as the P-Helm IVP side of it. And that'll sort of fill out perhaps the rest of the puzzle here of how this trail example works. So today's homework, we'll look at essentially extending this trail example to add a command message so that the operator on the top side can now tell the USV what to do. And you'll get the comms part of that filled out in the homework, and we'll do the autonomy side tomorrow. So before you go, I want to just show you one last thing here. which is this version of this diagram is automatically built for you using the static analysis tools in the build directory. So if I go into build, share, interfaces, figures, there's a whole bunch here, but the trail deployment is the one we want to look at. So if I open up the trail interfaces PDF, you'll see this is the view of, and I apologize, it's small, but we can zoom around. This is the actual view of that same figure I was showing you, but as generated from the code. So AUV0 is publishing AUV nav, subscribing to USV nav. The USV is publishing USV nav. Where's the top side? Top side's over here. Publishing USV nav and AUV nav picked up by the top side. And AUVN is the same as AUV0. And so the difference between this and what I was drawing for you earlier is that this is generated from the code. So if the code's wrong, this will change, and you can start debugging from there. So you may find this interfaces file very useful when you start adding in your own publishes subscribes. So apologies for going long. Thanks for so much for those of you who stuck around. Thanks for everyone who's watching this and recording. Thanks again to the sponsors here. And please, if you have any questions at all about the stuff I presented today, please put it in the Slack or come on to office hours. You don't have to have problems to join office hours. If you just want to talk about something or you want to talk about how you could use Goby in a particular scenario, feel free to jump on and we'll try to answer everything you can. So thanks again. I'll catch some of you later. Otherwise, I'll see you all tomorrow.